So let's look at this figure, which is a nice 91-day running RMM variance for a number of years, for a few decades here, going from 1981 through 2016. This indicates that there are potentially low frequency variabilities in MJO. Just think of it as a number of MJO events in each year, whereas the year itself, obviously November to April, means you're straddling the calendar year, but it doesn't matter. So when you look at it this way, this is the RMM variance, so it is RMM1 squared plus RMM2 squared. Remember EOF 1 and 2 of the OLR and 850 and 200 hectopascal zonal winds. So this is the relation can be kind of looked at in terms of El Niños. 82-83 was a very strong El Niño. 86-87 was an El Niño. There were smaller El Niños here. 97-98 was a monstrous El Niño again. And then let's say we had 15-16 was a monstrous El Niño. What you see is essentially that there is no robust relation. Maybe there is a weakening of MJOs during an El Nino. This has been argued by some people looking at long-term correlations of sorts, but maybe La Nina has the opposite relation, but this relation is not very robust. But nonetheless, there are many studies that look at how MJOs may impact El Nino. And there the definition of MJO gets kind of murky, because there are what are called westerly wind bursts which happen in the western Pacific Ocean, which happen on a weekly time scale. They have a certain minimum wind speed, 8.5 meter per second or so, and they have to last for 7 days, in which case they are strong enough and the fetch is big enough for them to produce Kelvin waves, which goes off towards the east and affects the thermocline. And then the coupled feedbacks in terms of thermocline affecting SSTs, SSTs affecting surface pressure, changing the east-west temperature and surface pressure gradients, and then setting off what is called a Bjerknes feedback. If you don't know what it means, you can look up my podcasts on El Nino and Bjerknes feedback. Nonetheless, there the westerly wind bursts are systematically seen not only during El Nino years but even during other years. So they don't always produce an El Nino, but there seems to be a relation where the westerly wind bursts are able to push the West Pacific warm pool towards the east, and then they grow in their fetch and duration and maybe get stronger and so on. But whether those westerly wind bursts are really MJOs or there are some surges from the extratropics and so on have to be discussed separately. We won't get into that here. But the low frequency variability of MJOs has been looked at by many people, like Julius Lingo, for example. Nothing systematic has been found. Obviously, people also want to know whether global warming is affecting MJO characteristics in any way, and there are some papers arguing that the Western Pacific warm pool and the Indian Ocean side of the Indo-Pacific warm pool has grown in size because of anthropogenic forcing, and that has changed the MJOs in terms of its residence time in the Indian Ocean being reduced, and its time in the West Pacific maritime continent has increased, and so on. But we will leave it at that. But nonetheless, just best to remember that MJOs are part of this multi-scale system where you are going essentially from weather time scales like westerly wind bursts and of course precipitation into intraseasonal time scales and transitioning into interannual and maybe longer time scales as well. The other aspect that has to be looked at is how Madden-Julian oscillations themselves are feeding into lower frequencies and other aspects of global climate. This is a nice figure I picked from PML NOAA, but I think it was made by Kunio Yoneyama. I hope I got his name right, and maybe Chidong Zhang, who's at NOAA PMEL. So it is showing various features here that are presumably being affected by the MJO. So there is the Arctic Oscillation, Antarctic Oscillation, Antarctic Circumpolar Current. There are wildfires, cyclones. I already mentioned cyclones before as being cyclogenesis being more favorable in certain phases of MJO. This relation seems quite robust. The Indonesian through flow between the Pacific and the Indian Ocean dipole, which is the Indian Ocean version of the zonal mode or the El Nino mode. So El Nino is also affected by the MJOs, the westerly jet, the Seychelles Chagos thermocline ridge, which is a feature here which affects rainfall and cyclones and Rossby waves over the Indian Ocean, maritime continent, and Australian and Asian monsoons, South Asian and East Asian monsoons, winter conditions here, storm tracks, atmospheric river, which is a very prominent feature for rainfall and storms over California. They have some predictability because they travel over long distances and bring plenty of rain and snow over the mountains and so on. So floods here can be affected, and the weather and so on over these large parts all the way into Alaska, wildfires here. So West Africa, South America. So NAO, which is the North Atlantic Oscillation, is also affected, but there is also evidence that North Atlantic Oscillation may be affecting MJOs. At least the phase of MJO tends to affect the phase of NAO, which tends to be lower frequencies. It has higher frequencies but persists for longer periods than obviously MJOs, but MJO activity is affected by the phase of the NAO, and MJO predictability is also likely affected by the phase of the NAO and so on. So obviously this is a nice figure that basically argues that hurricanes, typhoons, cyclones are all affected by the MJO at synoptic time scales, and then many lower frequencies like ENSO, IOD, and atmospheric river and so on are also affected by the MJO. Let's leave it here and then come to the theories of MJO, and I'll also throw in a few ideas about the theories of the MESO, or the monsoon interseasonal oscillation, which are often also mixed in with the boreal summer season interseasonal oscillations, BSISO, boreal summer interseasonal oscillations. So we'll do that in the next podcast.